Hello everyone, I am Enrique Fuster. This presentation consists of the analysis of the photovoltaic potential of the residential building sector in the city of Valencia, Spain. The paper was done in the Institute for Energy Engineering of the Polytechnic University of Valencia. Well, let's start with the index. First, I will explain the motivation and contributions of this study inside the introduction section. Then I will describe the bottom-up model in the methodology. Finally, I will go through the main results obtained and their conclusions. I hope you will find this content interesting. Let's start with the introduction. Just to give you a background, we have reached the grid parity and photovoltaic energy is competitive against other conventional technologies, mainly due to the reduction of the installation costs up to 90% during this last decade. In addition, self-consumption has been promoted by regulation. On the other hand, we have the challenge of a growing electricity demand. Currently, electricity constitutes 40% of the final energy consumption in buildings, and this rate will increase together with the incorporation of the electric vehicle and a greater penetration of household appliances. Photovoltaic energy represents an interesting solution to face this challenge, mainly because there is a high solar resource. Self-consumption also allows to build smart grids and promote on-site energy production, as well as its proximity to the consumer can help to develop a social awareness toward the renewable energies. So in the end users can play an active role in the electricity sector. In the research of the photovoltaic assessment in urban areas, the shadows must be taken into account. Usually top-down methods are employed using LiDAR data files and raster or vectorial maps. Most of these studies are circumscribed on the technique potential, but there is not many large-scale studies in cities focused on the economic and profitability area. These kind of studies must be really helpful to energy planners, authorities and companies to identify quickly which districts and specific buildings are the most suitable in economic terms to install a PV facility. The aim of this study is to cover this gap, so here we provide a bottom-up techno-economic model which estimates for each building the profitability in energetic, economic and environmental terms. We have carried out the simulations in a sample of more than 1,000 buildings and included identification of which characteristics of the buildings affect the most to the economic payback. Once explained our motivation, let's see the methodology employed in our model. Basically, our techno-economic model has been performed using R programming code, an open-source programming software which stands out for its versatility and the capability to simulate large samples. The program has as main input the building rooftop coordinates and provides the results of the performance in terms of energy, economic and emission savings of the PV facility in hourly values throughout its lifetime, assumed in 25 years. If we look inside the model, it is constituted by 5 different submodels. First, we use an isotropic irradiation model. Second, with the spatial urban model, we include the shadow losses due to nearby buildings by using LiDAR and cadastral data. Then the irradiation is converted in electricity production, assuming a standard performance ratio and photovoltaic efficiency in the production model. The demand model allows us to match the production with the load curve of building based on cadastral information. And to finish, we can calculate the cash flows and investment costs in the economic model, and the amount of emissions avoided in the emissions model. In the results section, first we will see the validation results of the model using a reference software, followed by the appliance of the model on a sample of buildings analyzing their energy, economic and environmental results. We will continue to identify the most influential factors on the economic payback and discuss different approaches to increase the profitability of PV facilities by applying subsidies or configuring energy communities. The hourly radiation results on a given tilted surface, including the shadows cast by nearby buildings, have been compared with the ones provided by the System Model Advisor software developed by the National Renewable Energy Laboratory, using the same scale and profile of several buildings and irradiation series as inputs. The resulted deviation from the yearly global radiation taking into account shadows is between 0.9% and 3% for different combinations of tilt and azimuth angles. The urban area of the city of Valencia has been the scenario to apply the techno-economic model. Currently, the public administration is interested in the deployment of the PV facilities in the city, so these kind of studies can provide a preliminary idea about where to focus the investments wisely. It was taken a simple random sample, representative enough, composed by 1,000 multi-story buildings and 100 single-family houses. With a first glance at the map, we can see the spatial distribution of the economic payback of the simulated PV installations. We can notice that the city center area presents the worst profitability results. We will see the reason of this in the following slides. Let's get into the simulation results of this sample. First, if we pay attention to the profitability reflected on the economic payback, we can see a high contrast between multi-story buildings and single-family houses. The first ones present an average payback of almost 12 years, and the second ones mostly surpasses the life cycle of the facility. We can notice that over 50% of the multi-story buildings have paybacks under 11 years, so this is the most interesting typology in economic terms. In contrast with the previous values, the required time to recover the emissions produced in the fabrication and transport of the facilities are recovered in a few years. So for the promotion of facilities in this type of difficulty, it would be really valuable to study the grand implementation. So with more results, we can see that the renewable fraction and the amount of surpluses injected to the grid in the single-family typology tend to be higher than in the multi-story one. In multi-story buildings, the relationship between surpluses and productions present very low values because they are characterized by reduced rooftop areas, so the totality of the energy generated is intended to partially cover the high level of electrical demand. Consequently, very rarely, the generation exceeds the demand producing surpluses introduced to the grid. On the other hand, single-family houses usually have low consumption amounts, so most of the production is self-consumed, with its consequent increase in the renewable fraction in the surpluses. In addition, shadow losses registered in single-family houses are usually higher than the multi-story buildings. This is normally related with the height or number of floors, since single-family usually have one or two and multi-story 3 or more. If we aggregate the previous results by typology, we can see the impact of the self-consumption for the sample analyzed. Around 13% of the total current energy consumption of these buildings could be replaced by on-site renewable PV energy. We are just talking about 1,000 multi-story buildings, and the entire city has over 20,500 buildings. We can notice this is not a negligible amount of energy. We have similar renewable fraction for single-family houses. With the simulation results, we have identified 3 variables that can explain the difference in the economic payback results among different buildings, in the following order of importance. First, the size of the installation. In other words, the amount of available rooftop area directly related with the installed power, whose cost per unit decreases while the power installed increases. Second, the shadow losses, which depends on the surrounding buildings and affect directly to the potential of the PV production. And third, the load curve of the building, which is related with the amount of surpluses, since a low electricity demand will increase this value and vice versa. To determine the degree of the influence, we developed a multiple linear regression model in which the economic payback was predicted by these 3 previous parameters. Here we have the correlation matrix obtained for this regression model. We can see surplus remuneration does not play a big role because surplus prices are quite low in comparison with the electricity prices from the grid. The plot on the left side shows for the simulated sample that lower power unit cost in dark blue provides the best results on payback. We can also notice the growing tendency of payback when the shadow losses increases. The reason why previously in the map of Valencia we have seen that the facilities of the city center have the worst profitability results is because most of the buildings have small rooftop areas and many shadow losses. One way to reduce the economic payback is by reducing the investment cost by applying a certain amount of subsidies. We see for the multi-story building sample that the economic payback reduces around 1.7 years each 10% of the subsidized investment costs. In single-family houses, we see that this reduction increases faster with the percentage of the investment subsidized. Local authorities must study this option to promote self-consumption. We have seen in the simulations that the buildings with best profitability are those with high consumption and large rooftop areas due to the economy of scale. The grouping of consumers around a single PV installation, also known as energy communities, seeks to achieve that effect. In this case of study simulated, we have a multi-story building with several dwellings and shops with a payback of 10 years, and a single-family house that has a payback of 19 years, economically unviable due to the high installation costs. One way to improve the profitability is by sharing the facility, in other words, by supplying electrical energy to the single-family house with the PV installation of the multi-story building. The global payback of the facility is reduced to 9 years. Mainly, the economy of scale of the residential building is used to keep the installation costs. Let's see the main conclusions of this work. Firstly, we have seen the calculation method and assumptions of the bottom-up economic model to assess each building individually. Secondly, we have applied that model to a significant sample of residential buildings, in which we can appreciate that the typology of multi-story buildings is the most interesting one in terms of profitability. The renewable energy produced for both cases is not negligible, as the renewable fraction value shows. Paying attention to the economic area, we have also quantified the degree of influence of the most important variables. It is necessary to highlight the relevance of the economy of scale and shadow losses on the economic payback, and the little importance of surplus remuneration. We have also discussed several alternatives to improve the profitability, which we will continue investigating in next studies. And going a little bit deeper in the building characterization, we can conclude that the buildings that present best profitability results share the following characteristics, which have been previously discussed. Large rooftop areas allow us to install more power with lower unit cost thanks to the economy of scale. Normally, high buildings present reduced shadow casted by nearby buildings. Buildings with high levels of electricity demand tend to profit in a high percentage from on-site energy generated from self-consumption. So the amount of surpluses is really low, and all the energy generated is translated into energy and bill savings. And obviously, it is necessary that an important part of the load matches with the PV production. Buildings with consumptions during the sun hours are the most benefited. These characteristics are usually gathered by typologies such as multi-story residential buildings and commercial buildings. Therefore, these are the ones that can benefit the most from self-consumption. As additional conclusions, we can say that surplus injection to the grid does not play a significant role in the economic balance because of the low remuneration prices in comparison with the electricity bill. Consumption levels by joining multiple buildings can be benefited by a single self-consumption facility and improve its profitability. Subsidies play an important role in the residential sector to promote private self-consumption initiatives. Finally, just to say that this work will be implemented as part of a tool developed on the chair of urban energy transition in the Institute for Energy Engineering at the Universitat Politécnica de Valencia, and that hopefully will soon convert into the spin-off Impacte. The tool will be a geographical information system web-based tool as shown in the video for facilitating the energy transition to municipalities. You can learn about the saving potential using heat pumps energy on the session shown in the slide. This study was developed thanks to the support provided by the Chair of Urban Energy Transition of the Universitat Politécnica de Valencia. Thank you very much for your attention. Finally, if you require more information, you can contact me via email.